Up to now we have discussed finite automata, the formal definition of the finite automata, and the finite automata with two types, non-deterministic finite automata and the deterministic finite automata. And also we have seen the conversions, non-deterministic finite automata to the deterministic finite automata, NFA with epsilon to DFA and directly from NFA to DFA. And also we have seen the minimized DFA using two methods, using equivalence partition method and the Myhin-Nerod theorem, and also we can call it as the table filling method. Next we will see finite automata with output. Finite automata with output that can be categorized into two types, Mealy machine and the Moore machine. So here the Mealy machine, it has 7 tuples. We will see the definitions of the Mealy machine and the Moore machine. First, the Mealy machine means it is a one type of finite automata with output. Here the output depends only on the present state and the present input. Present state and the present input. When we see here the formal definition of the Mealy machine, we have 6 tuples, Q, summation, delta, gamma, lambda, Q naught. Q means finite non-empty set of states, where sigma is input alphabets, delta is the output alphabet. Next, gamma is the transition function mapping, that Q into sigma to Q, and lambda is the output function mapping, that is Q into sigma to delta, and Q naught is the initial state. Whereas in the finite automata we have seen the 5 tuples. The same thing, whereas in the finite automata with output we have the 6 tuples. Here we have seen the output alphabet and also output function mapping compared with the finite automata. When we come to the same Moore machine, coming to the formal definition of the Moore machine, so again we have the 6 tuples, because Moore machine is also the same finite automata with output, but here the output depends only on the present state itself. Mealy machine, output depends on the present state and the present input. Moore machine depends only on the present input. So that is the main difference between Mealy machine and the Moore machine. So according to this Moore machine, we will see the formal definition: Q, sigma, delta, gamma, lambda, Q naught. Same Q is the finite non-empty set of state, sigma is the input alphabet, delta is also the output alphabet. So next lambda, that is the transition function mapping, is different coming to the Mealy machine and the Moore machine. So whenever we have the transition function, that is output function mapping, here the output depends, the Mealy machine output depends on the present state and the present input. Coming to the Moore machine, output depends only on the present state. So that means Q that derives delta, so it depends on only the present state. So here when you see the Mealy machine, present state and the present input, here the output depends on the present state and the present input. Here the output function mapping depends only on the present state. That is only the difference between the Mealy machine and the Moore machine. Whenever we have finite automata, normal finite automata, we don't have one output alphabet and the output function mapping. Here we have output alphabet and output function mapping. So Mealy, present state as well as present input. Moore machine, output depends only on the present state. So this is the transitions function in the Mealy machine and the Moore machine. Here we will see the Mealy machine. We will see it one by one. So if you see the example of the Mealy machine here, this is the Mealy machine diagram. So when we observe these, it's like normal finite automata, but it has output. Whereas in the Mealy machine, the output, so whenever we have the input alphabet, so that beside we have the output alphabet. That is the Mealy machine. Here A, whenever we are transmitting A to B on input alphabet 1, we have the output alphabet as 0. The same, whenever we have the input alphabet 0, the next state is D, output alphabet is 0. Next, coming to the B, whenever we have the input alphabet 1, so output alphabet is D when transmitting to D. That means this is the example diagram that we have taken. Based on this, we have to go with the transition table. So I will show you how we have to take this transition table. First, we have to write the present states A, B, C, D. So I have taken A, B, C, D. Now we will fill this table according to our Mealy machine diagram. See here, next state A on input 0, next state A on input 0, the next state is D. A on input 0, the next state is D. So what are the input alphabet? Beside is output alphabet, right? What we have? 0. 0 is the output. Next A on input alphabet 1. A on input alphabet 1. The next state is B. The output is 0 here. Next, coming to the B. The next state on input alphabet 0. This is on input alphabet 0. The next state is A. Output alphabet is 1. B on input alphabet 1. The next state is D. Output is 0. C on input alphabet 1. C on input alphabet 0. The next state is B and the output is 1. C check on input alphabet 1. So the next state is A and the output is 1. Next D. Next state on input alphabet 0 first. Next state is D itself. This is the output alphabet, that is 1. D on input alphabet 1, the next state is C, output alphabet 0. Like that we have to take the transition table. First we will write the present state. On input 0, we have to write next state as well as the output. On input 1, we have to write the next state as well as the output. Whereas in the normal finite automata transition table, we have taken the present state and the next state on input alphabets. But here, whereas the finite automata with the output, whereas in the Mealy machine, here we have taken present state, next state with outputs. That is about the Mealy machine. So the formal definition of the Mealy machine. So you have to remember the transition function. It depends on the present state and the present input. So for the example of this Mealy machine, so how to write the transition table, we have to know.